In this lesson, we will find special products of binomials. Alright, suppose we wanted to multiply these two binomials together. Remember, binomials are polynomials with two terms. Each one of these is called a monomial. X is a monomial, 3 is a monomial, x is a monomial here, and negative 2 is a monomial here. Suppose we wanted to multiply these. From class, you should remember that we use the FOIL method to multiply such things. So using the FOIL method, I get the first product is x times x, which is x squared. The outer product is x times negative 2, which is negative 2x. Inner product, 3 times x. And the last product, 3 times negative 2 is negative 6. Combining like terms, I have negative 2x plus 3x, which gives me positive 1x. So I end up with the product of these two binomials is x squared plus x minus 6. I can do the same thing with these two binomials. My first product is x squared, x times x squared. My outer product, x times negative 12 is negative 12x. Inner product, negative 5 times x is negative 5x. And my last product, negative 5 times negative 12, is positive 60. Combining like terms, I get the following trinomial. Now, suppose I need to multiply this through. This is x plus 3, the entire binomial squared, which is just x plus 3 times x plus 3. I can use the FOIL method once again, getting x times x squared, x times 3, 3x, 3 times x is 3x, and my last product, 3 times 3, is positive 9. Combining like terms, I get x squared plus 6x plus 9. Now, what I'd like you to do is look for a pattern between my original product and the resulting trinomials. See if you can find a relationship between these monomials here and the resulting monomials here. Looking at another example, if I wanted to multiply x plus 4 squared, this is just x plus 4 times x plus 4. Once again, using FOIL, I get this. Here's my first product, my outer product, my inner product, and my last product. Combining like terms, I get this trinomial. Okay. And if you notice here, it looks like the constant term is somehow related to the original constant term in my binomial. Similarly here, my x term looks like it may be related to my constant term from my original binomial. Does that same pattern hold true here? Well, let's look at a couple more examples. Suppose I wanted to multiply these two binomials together, x plus 5 times x minus 5. Once again, using FOIL, my first product would be x times x, which is x squared. My outer product would be x times negative 5, which is negative 5x. My inner product would be 5 times x, which is 5x. And my last product would be 5 times negative 5, which is negative 25. Combining like terms, notice I have negative 5x plus 5x. Which end up canceling each other out, and I get x squared minus 25 as a result. Once again, your goal should be to find a pattern between the original monomials in the product I was seeking and the result here. Do the same thing with this one. If I FOIL this, I end up getting x squared minus 81. Once again, see if you can find a pattern between my original product and the resulting binomial in this case. So, special products. The special products ax plus b squared and ax minus b squared, and these two binomials multiplied together can all be found using the FOIL method, just like we did in the introduction. Now, we give these special names. The product ax plus b squared and ax minus b squared are called the squares of binomials for obvious reasons, because we're squaring binomials in each case. Okay, and the product, this product here, is called a sum and difference product, because notice in one case the binomial is a sum, and in the other case the binomial has a difference, with the monomials though being the exact same. The only thing that's changed is that we have a sum here and a difference here. Now, let's multiply this through so that we can once again see if we can materialize a pattern with the resulting product. So 2x plus 5 squared is just 2x plus 5 multiplied by itself. Okay, FOILing, I get 2x times 2x, which is 4x squared. My outer product is 2x times 5, which is 10x. My inner product is 5 times 2x, which is also 10x. And my last product is 5 times 5, which is 25. So combining like terms, notice I have two like terms here, 10x plus 10x, this gives me 20x. So my result is this trinomial here when I square this binomial. Once again, see if you can find a relationship between the monomials in the original expression and the monomials in the resulting trinomial here. Is there some kind of pattern that you can find? Looking at another example, the only thing I've changed here is that in the last example, 1a, we used 2x plus 5 squared. This time we're doing 2x minus 5 squared, which is just 2x minus 5 times 2x minus 5. Foiling, I get 2x times 2x, which is 4x squared, times my outer product, which is 2x minus 5 minus 10x, and my inner product is negative 5 times 2x, which is 10x, and my last product, negative 5 times negative 5, positive 25. Combining like terms, I get minus 10x, that's negative 20x. So this is my resulting trinomial. See if you can find a pattern once again between the original monomials and the resulting trinomial. Okay, one more special case. Let's say I have 2x plus 5 times 2x minus 5. Remember, this is called a sum and difference product, whereas the previous two were called squares of binomials. Okay, so let's see what we get when we FOIL this. Well, I get 2x times 2x, which is my first product, is 4x squared. My outer product is 2x times negative 5, which is negative 10x. My inner product, 5 times 2x, which is positive 10x. And my last product, 5 times negative 5, which is negative 25. Combining like terms, notice that these essentially go away because I end up getting 0x. So my resulting expression is 4x squared minus 25. So the product of these two binomials is this. Once again, look for a pattern between the original binomials that we multiply together and the monomials in these compared to the monomials in this expression here, its product. Remember to come to class prepared to discuss and answer the answers to the reflect questions as always. Okay, so these special products appear often enough that we actually tabulate or put into a table the patterns that we see. So notice whenever we have a sum and difference product, we end up getting this expression as a result. You may have noticed this from the examples that we did. And these are the other patterns here. You should definitely record these in your notebook because we're going to be using them for the next couple lessons. Okay, so in this example, we're going to justify the sum and difference rule and then use it to find the product. If we go back, the sum and difference rule says that if I have a sum multiplied by a difference, then I just basically get the square of the first monomial minus the square of the second monomial. When I was in school, I learned this as the difference of squares is equal to conjugate pairs. These are considered conjugate monomials because I have a sum here and a difference here. So what we're going to do in this example is we're going to justify that rule. Okay, so let's start with an arbitrary product of a sum and a difference. So these can be anything now. A plus b, a minus b, a and b can stand for anything. It could be a constant term, it could be a variable term, it could stand for anything. So, but we're just going to call them a and b. So let's see. If I FOIL this special product, I get my first product is a times a, my outer product is a times negative b, my inner product is b times a, and my last product is b times negative b. Okay. Now I can simplify this expression since I could write a times a is a squared. I could write a times negative b as negative ab, and I'll just leave ba the way it is. And of course b times negative b is negative b squared. Okay. Now simplifying this further, notice that these two here are like terms that end up canceling each other out, and I'm left with a squared minus b squared. So I've just justified the rule. The sum and difference rule says that the product of a sum and difference is just equal to the square of my first monomial minus the square of my second monomial. Okay, so you can see how this is related. Now we're going to use this rule to find the product rather simply without using the in-between steps anymore. You'll see how this is used in a second here. So let's use this rule so that we can avoid the intermediate steps and get right to the answer. So according to our rule, okay, the product of this sum and difference is just going to be this monomial squared minus this monomial squared. Okay, so I write this in terms of my rule. 4x squared takes on the role of A, and 15 takes on the role of B in the difference rule, sum and difference rule. So I end up getting 4x squared squared minus 15 squared. Simplifying this, I get, using my integer exponent rules, I get that this expression here is equal to 16 times x to the fourth minus 15 squared, which is 225. Okay, so what we talked about today is how we can find special products of binomials. You can use the distributive property, the FOIL method, or the special product rules to find special products of binomials. Okay, for your summarized activity, you should make a table for multiplying special products of the binomials, and your table should include each method, the distributive property, FOIL, special product rules, and an example of each method, and a list of advantages and disadvantages for each method.